Hey everyone. In this video, we will be discussing our review for Chapter 8, which is on what is called hypothesis testing. Okay, so hypothesis testing is a very formal way of talking about statistical experiments. It's extremely formal, extremely rigid. You want every single hypothesis test you do to have the same structure, which is what I'll be talking about here first. And so there's two methods. So I'll talk about that here. There's the traditional method, that's the one that we'll be studying. And there's the p-value method, which I haven't included any questions for in the work. So we'll just be talking about the traditional method. But you can read up on the book on the p-value method as well. And if you want to use that to come up with answers to questions, that's also fine. So let's look at what is the traditional method for hypothesis tests. Okay, so step one is to state the null hypothesis and claim. We'll talk about all these steps very in depth shortly, but I want to get the whole method down on paper first. And so number two is to find the critical value or values. From the appropriate table. Step three is to compute the test value. Four, we make the decision to reject or not reject the null hypothesis. And then step five is to summarize the results. So hypothesis tests are used quite often in statistics, higher levels of statistics, anything using statistical studies, very often use this very rigid form of testing called a hypothesis test. So first, let's go through each step, essentially, and go through examples as well. Okay, so let's go through each step in depth. Okay, so let me define these first. The null hypothesis symbolized by, this is called H sub 0. It's H with a subscript 0. is a statistical hypothesis that states that there is no difference between a parameter and a specific value, or that there is no difference between two parameters. So with the null hypothesis, always use an equal sign. Okay? The null hypothesis, you want to always use an equal sign. And so the null hypothesis is basically an assumption, a baseline, something to be tested. We're assuming this thing to be true, and then we're going to somehow test if it's not true or not to disprove it. So that's essentially what the null hypothesis is. You always state it with h sub 0, and then whatever the assumption is. We're assuming that the mean is equal to some number, or that a proportion is equal to some percentage, or something like that. We'll discuss those in the later sections, though. The important part is it's always going to be an equal sign, at least for this book. There are other books that use different notations. So you might see it a little different in some videos, I guess, if you look those up. But we're going to, for our purposes, just use equal sign. And the alternative hypothesis is essentially the claim. So the alternative hypothesis, symbolized by h sub 1, is a statistical hypothesis that states the existence of a difference between a parameter and a specific value, or states that there is a difference between two parameters. And for the alternative hypothesis, we're always going to be using a less than, a greater than, or a not equal to symbol, depending on the context of what we're trying to prove or disprove about the null hypothesis. Okay, so there's only a couple of instances that can occur for the alternative hypothesis, as we see here, less than, greater than, or equal to. And so let's look at a couple examples to highlight when to use which symbol. So I've got a couple examples here from the book. Let's go over these and try to find and determine what the null and alternative hypotheses are. So this question says, a medical researcher is interested in finding out whether a new medication will have any undesirable side effects. The researcher is particularly concerned with the pulse rate of the patients who take the medication. Will the pulse rate increase, decrease, or remain unchanged after a patient takes the medication? So what would our null hypothesis be here? What would our alternative hypothesis be here? Remember, the null hypothesis is stated with H sub 0. And in this case, oh, I guess they do give a little bit of additional information here in the book that I didn't see. Let me paste that in here as well. There's this additional piece of information that I didn't have. So it says, since the researcher knows that the mean pulse rate for the population under the study is 82 beats per minute, what are the hypotheses? Well, the null hypothesis, what is our assumption? What's our base assumption? We're assuming that the mean pulse rate for the population is 82 beats per minute. It's a mean, so we know the symbol for mean of a population is mu, and it's supposed to be 82. So our null hypothesis is that mu, aka the mean, is 82. Our alternative hypothesis, it's going to be mu is what? Less than, greater than, or equal, or not equal to. Which of the three symbols do we pick? It's about what is trying to be tested here. So it says the researcher is particularly it says, will the pulse rate increase, decrease, or remain unchanged? So they're not trying to see if it's only greater than. They're not trying to see if it's than 82. They're not trying to see if it's only less than 82. They're trying to see if it is changed, if it's different than 82. They're trying to just see if it's changed at all. So aka, this means we want to test if it's not equal to 82. So if you're just trying to see if something has changed, so when testing if something has changed, not specific change, not greater than, not less than, it's just has it changed at all, we use not equal to for our alternative hypothesis. Okay, so here it's very specifically saying, has it changed? Will it increase? Is the actual mean an increase of this, a decrease of this, or unchanged after they take this certain medication? And so that's when you use not equal to. Let's look at another scenario. A chemist invents an additive to increase the life of an automobile battery. If the mean lifetime of the automobile battery without the additive is 36 months, what would the hypotheses be? Well, it says the mean lifetime without the additive is 36 months. So that's our base. We're assuming that without the additive, that the mean lifetime is 36 months. So that's our null hypothesis. So what's being tested in this experiment? They're trying to see if this additive increases the life of the battery. So what are they going to be testing here? if the mean is greater than 36. Has the increase actually happened? So in this case, our alternative hypothesis, aka our claim, is going to be that mu is strictly greater than 36. Okay, and so we use the greater than symbol if we're looking for an increase. We use the strictly greater than symbol. So that's what our null and alternative hypotheses would be for this question. And another one here, a contractor wishes to lower heating bills by using a special type of insulation in houses. If the average of the monthly heating bills is $78, her hypotheses about heating costs with use of insulation are, well, she wants to, without the insulation, the average monthly heating bill of a tenant is $78. And she wants to lower that by adding some sort of insulation. And so she's going to be testing if the average is actually lower than $78. And so in this case, our null hypothesis, we're assuming before the insulation is added that the average monthly cost is $78. Our alternative hypothesis, we're going to test if it's actually true that this insulation will have an improvement on the monthly heating bill, aka lower. So it'll be mu is strictly less than 78. That would be our null and alternative hypotheses under these scenarios. So of course, when looking for some decrease, use strictly less than. And so these are pretty much, at least for the purposes of right now and in this class, the three scenarios that can occur. The null hypothesis always uses an equal sign. You're just assuming some base assumption to, base everything around, a starting point, if you will. And then we've got an alternative hypothesis, which reflects what the researcher is trying to test. Sometimes they're introducing some drug and they have no idea what's going to happen. Maybe it'll increase, this parameter or decrease this parameter. They have no idea what's going to happen. Other times they have some inclination about what might happen. And, when they don't have any idea about what's going to happen, that's when we use the not equal sign. When they're testing if it's, greater than or less than some actual value, we use greater than or less than. And that's pretty much step one of the hypotheses test. Always you have h sub 0 using equal sign, h sub 1 using not equal to, greater than, or less than. Okay, so step 2, we've got to find the critical values, or values. Okay, so let's talk about this for a bit. This is dependent on the significance level. This goes back to our confidence intervals, essentially. Right, we can only be so confident in something, and we've got to have some tolerance about it, and whether accepting it or not. Right, we had confidence levels of 99.5% or, whatever it may be. And this significance level influences where the critical values are going to be. So let's talk about errors, type 1 and type 2 errors, to help kind of think about the errors that can happen and how bad those errors are. Well, let's look at an example where we define our null and alternative hypothesis as follows. We've got some defendants, and we're assuming that he's innocent. That makes sense, especially according to American law, where you're innocent before proven guilty, right? So we're assuming that the person is innocent. We've got to disprove that to find them to be guilty. And our alternative hypothesis is that the defendant is not innocent. AKA guilty, right? It really helps to visualize in a box. So there's 4 possibilities. Let's assume this column means that h sub 0 is true, and this column is h sub 0 is false. And here we'll talk about whether we reject or fail to reject. Okay, so let's look at the top left box first. Here we are saying that the person is innocent, but we're rejecting it actually. We're actually rejecting it. So in this case, the person's innocent. In this case, the person's guilty. I guess I could even put that here. That'll help make this a little bit more clear. So this is our innocent column. This is our guilty column. And this column is basically we convict them. We put them in jail. And this one we acquit. Or we acquit them, which means we don't put them in jail. Sorry, I made it a little bit clearer now. So the top left box represents an innocent person that we put in jail anyway. This is what's called a type 1 error. Right, so a lot can go wrong to make an innocent person be shown to be guilty. Right? Maybe they had a really bad lawyer. Maybe evidence was mishandled. Something like this, right? Those things can happen. However, if they're guilty, so the second, if we look at the top right column, if they're guilty and we convict them, then that's right. That's the correct decision. Let's look at the other column, the other boxes. The bottom left box, it was an innocent person and we acquitted them. Well, that's also a correct decision. However, if the person's guilty and we acquit them, this is another type of error that can occur. This is called a type 2 error. They use Roman numerals usually. And so a type 2 error, a guilty person being acquitted, a lot of times that can happen as well. Maybe there wasn't enough evidence to prove them guilty beyond a shadow of a doubt or whatever. Hung jury or something like that. So, there's many different ways that a type 1 and type 2 error can kind of be manifested depending on what the null and alternative hypotheses are. And depending on the significance level, essentially this allows us to define significance level. Okay, so the level of significance is the maximum probability of committing a type 1 error. This is symbolized by alpha. It's the first letter in the Greek alphabet, alpha. A quick note, I guess. A type 2 error is symbolized by beta. I guess that beta was fine. Yeah, beta. But type 2 errors are much, much harder to kind of account for or calculate. And usually, like, increasing one makes the other one decrease. They have, like, kind of an inverse relationship with each other. Okay, but alpha is the important one. That's the one that we'll be talking about and using to come up with the critical regions. So still talking about step 2 here, finding the critical values. And I just wanted to do a little spiel about type 1 and type 2 errors. I did put a couple questions in there about those. And this is kind of a really good way to think about it, this specific example, I think. Okay, and so typical values of alpha are, 0.1, 0.05, 0.01 usually. There can be other levels, of course, but these ones are used the most. Okay, sorry, I'm just trying to think of the best way to describe this. Let's just, for an example, for examination. Okay, so we're going to assume that alpha is equal to 0.1 for the drawings that I'm putting here. So this is what a one-tailed test would look like. We use a one-tailed test whenever it's a less than or greater than symbol in our alternative hypothesis. A less than, it's going to be a left-tailed test. A greater than, it's going to be a right-tailed test. Okay, so let's say it was a left-tailed test. Let's draw the picture. So our significance level, we're assuming a significance level of 0.1 or 10%. So that means the inner amount is going to be the other 90% of the data. And the left tail is going to represent 10% of the data. Right? Again, this is when alpha is 0.1, aka 10%. It kind of represents the area of our critical range. Remember, the area under this curve is 100, or I'm sorry, 1 or 100%, right? Because it represents all of the data values. So for a left-tailed test, it would look like this, and this would be our critical value. And this would be our critical range. Okay, and so this is how to find it for a left-tailed test. For a right-tailed test, again, if we're assuming for our discussion here that alpha is 0.1, it always helps to draw a picture with almost every single question. If you find yourself having difficulty, make sure you do this because it really, really helps. So for a right-tailed test, if our alpha is 0.1, right, this would be 90% of the data, and this would be 10% of the data again. And so this would be our critical value. Whatever value is represented, is the cutoff essentially of the top 10%. And then, of course, this would be the critical range. And so this is what it's going to look like when it's a one-tailed test. If the significance level changes, you're going to have to change your picture, and that will change what the critical value is. But again, always try to draw a picture. You cannot believe how much it will help you when doing these. There's another type that we can get, which is called a two-tailed test. And this is for the scenario of less than or equal to symbol. The last one was for less than or greater than. A two-tailed test, it's when it's not equal to. So let's again draw a picture and see why it's called two-tailed and how to find the values. Well, if we're assuming that our alpha is 0.1 again, that means, right, alpha being 10%, the rest of the data would be 90% again. So this would be 90% of the data. And then anything in these two tails would be within the critical range. right? This would account for 5% of the data. This would account for 5% of the data, because you've got to cut the remaining, you've got to cut the alpha of 10% in half, aka 0.05. But it's best to, again, draw a picture. The picture is really, really what will help you when coming up with these values. And then, as usual, the critical values will be at these, these are the cutoffs, essentially, of being in the critical range or not. So those are what the critical values are. It's the cutoff of the critical range. And these critical values are going to have, they're going to be the same magnitude, right? The one on the left is negative, the one on the right is positive. So you don't always have to find both if you're doing a two-tailed test. You could just find the one on the left because that's the easier one to find. It's the negative. And then the one on the right is going to be the positive of that. But you could also just calculate it and you'll see, oh, I get the positive value. It's the same thing. And so this is what to do to find the critical values if it's a two-tailed test. So again, this concludes step 2, but let's just do a brief overview. So let's assume we've got our significance level. It could be 0.1, it could be 0.05, it could be 0.1, doesn't matter. You're going to need to look at the table anyway. And so draw a picture. Alpha, it represents, again, the maximum probability of committing a type 1 error. So it's kind of like, is it so far out of our acceptable range to reject the null hypothesis? Is it so far out of just possible error that we have to reject it? This is like our tolerance level, essentially. Same thing with our confidence level interval. You can, in statistics, you can never be guaranteed of anything. That's the whole idea here. And alpha is just our tolerance level. And depending on what the tolerance level is in the hypothesis test, tells us how accurate or how confident in the result we can be. It goes directly back to confidence intervals. And so if we have our alpha, then depending on if it's a one-tailed test or a two-tailed test, we find our critical value by drawing a picture. It really helps. I can't stress you enough. Draw the picture to come up with the critical value and the critical range in this step. Otherwise, it's really easy to come up with the wrong critical values. Okay, so that's step 2, really, really long, difficult step. Step 3, remember step 3 is, I guess it's to compute the test value. So this is going to be the value from a specific test, and we're going to see, essentially, if this experiment, this specific experiment, if the data in this experiment leads us to rejecting or accepting the null hypothesis. That's what the test value does. The test value brings all of the data together and lets us know, that's what we compare to the critical range. We'll see if the test value of the experiment is in the critical range. If it is, we essentially reject. So step 3 is to just compute the test value. And I guess this is highly dependent on the study. So this changes on whether you're looking for a mean or a proportion or et cetera, et cetera. So essentially, this is explored more in sections. This is what we talk about in the upcoming sections. we explore how to get the different test values that we'll be computing and how to do those. So that's essentially the next sections. We'll do plenty of examples of those in a bit. 8.4, or I'm sorry, step 4 is to make our decision. Okay, and so essentially here's what we're going to do. If the test value lies in either of the critical ranges, either critical range or ranges, if the test value lies in the critical range, we reject the null hypothesis. Essentially, the data is so far skewed that the thing that we're testing definitely had an influence or something like that. The insulation example. Say it decreased their monthly expenses by $30. Then that would be so statistically significant that we could say that we could reject the null hypothesis in a way. So if the test value is in the critical range, reject. If the test value lies in the non-critical range, we do not reject H sub 0. And that means the base assumption stays. We were not able to disprove our base assumption, essentially. And that's step 4. Not a hard step. You just have to, again, there's only one thing that can happen. You can either reject H sub 0 or accept or fail to reject H sub 0, aka do not reject H sub 0. I know it's a weird way of saying it. I know, very pedantic. But again, these hypothesis tests are extremely formal, extremely standardized, very rigid. And then step 5 is to summarize the results. And, what I'll do for this is I'll usually say at a significant level of, whatever alpha is, we have or do not have sufficient evidence to support the claim that blah, 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 whatever is being tested. They just want some sort of summary. So I would, at a significance level of alpha equal to, say, 0.1, we have sufficient evidence to support the claim that blah, 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 whatever H sub 1 is, or we do not have sufficient evidence to support the claim that blah, 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 again, whatever H sub 1 is. So no need to write like an extremely ridiculous summary. It could be very, again, formulaic like this. You could do it every single summary in this exact same manner, quote, verbatim, essentially. And this concludes section 8.1 on, the anatomy, essentially, of a hypothesis test. Very important. Every single time you do a hypothesis test, you're supposed to very clearly outline these 5 steps. And I will show as examples next on how to do that in sections 8.2, 8.3, and 8.4. This section, again, was just going about the overview and how you should approach every question in 8.2, 8.3, and 8.4. So I hope that's a good overview of hypothesis tests in general. Let's go to section 8.2, which is on the z-test for the mean. Okay, so we want to use this when sigma is known. So with these hypotheses tests, where a lot of the time we're not learning anything new, we're just kind of contextualizing stuff that we've already learned into a very formalized output, essentially. So a lot of the stuff here we've already discussed. We already know the formulas. No new formula here or anything. And so the formula, as we've discussed before, is that the z-score, or z-value, is x bar minus mu over sigma divided by square root of n. This is what's going to give us our test value, right? This is how we compute the test value. Okay? So let's go ahead and get some examples of how to do hypotheses tests for the mean for z-tests. I'm sorry, for when sigma is known. So I've got a question here. A researcher believes that the mean age of medical doctors in a large hospital system is older than the average of doctors in the United States, which is 46. Assume the population standard deviation is 4.2 years, and a random sample of 30 doctors from the system is selected, and they find the mean age of the sample is 48.6. Test the claim at a significance level alpha of 0.05. So this part is what lets us know we want to do a hypothesis test. This is saying do a hypothesis test and use alpha of 0.05 for your significance level. So let's go ahead and do that. Step 1, we've got to state our hypothesis and claim. Null hypothesis, sorry. So what's that going to be here? Go ahead, try to pause it. See if you can figure it out on your own. What our h sub 0 is and what our h sub 1 is. Well, h sub 0 is like our base assumption. And we're talking about means here, so it's going to be mu is equal to, and what are we assuming is our mean, essentially? We're assuming that it's 46 because that's the average age of doctors in the US. Okay, some base level assumption, right? We're assuming that the average age of the doctors in the hospital is 46 because that's the average age of doctors in the whole US, essentially, is what we're saying here. And what is the researcher testing? The researcher believes that the mean age of medical doctors in a large hospital system is older than that. So we're going to be trying to test to see if this is bigger. That's our claim. So you really got to look at the question and try to pick out this information very carefully. So that's our null hypothesis and alternative hypothesis, aka claim. That kind of summarizes what the researcher is assuming and what they're testing. So very important information. That's why it's the first thing told. Step 2 is find our critical value or values, or the critical range, if you want to say. So we look at our significance level. And the significance level, alpha, is 0.05. And this is a right-tailed test because we're doing mu greater than 46. So we want this to be 5%. And that means this to be the remaining 95%. And this value here is going to represent the cutoff of our critical range. Anything in this area, essentially, this is our critical range. And this endpoint right here is going to be the critical value. So we're doing z-scores here. So we've got to, unfortunately, again, use the z-tables. And z-tables, since they give the area to the left of a value, and we're looking for this value right here, we're going to be looking for the z-value that has an area to the left of it closest to 0.95, aka 95%. We want to find the z-value such that 95% of the data is to the left of that. Okay, so we've got to go to our positive z-table here. We find the area closest to 0.95, and that will be our z-score. Also, you can memorize the z-scores for 0.01, 0.05, 0.1 if you like, because they are used very often. But you do want to be able to calculate any z-score, any critical value or necessary. Let me just get the table real quick. Okay, so I've got my z-table here. Again, we want to look for what's closest to 0.95, because we're looking for the point such that the area to the left of that point is 0.95, or closest to 0.95. So I guess either of these would work, but the book defaults to 1.65. I guess you could pick either of them technically, or you could split the difference. But for a significance level of 0.05, we typically end up using 1.65. Okay, so the critical range is anything bigger than 1.65. This is a z-value. Let me just move this down or a different spot. It turns out that this critical value ends up being 1.65. So that's our critical value, 1.65. Step 2, done. Now we go to step 3, which is to compute the test value. And remember, for this, we use the formula x bar minus mu over sigma divided by square root of n. Just need to pick out all this information from the problem. So let's see here. Our mu is 46. We knew that already. What's x bar? Remember, x bar is the mean of the sample. So a random sample of 30 doctors had a mean of 48.6. That's x bar, 48.6. We also need to know sigma, the population standard deviation, which is 4.2 years, they tell us. And n, the number of people in the study, that's 30. Plug all this in, that will give us our test value. Make sure to do it in the calculator correctly. I do see a lot of students incorrectly calculating the z-score just from feeding values into their calculator improperly, like not using proper order of operations. So make sure to use parentheses, use excessive amount of parentheses if you like. So this is over 4.2 divided by square root of 30. I'll round it to 2 decimals because generally that's what how many decimals we go to for z-scores. So the numerator 48.6 minus 46 divided by the denominator, that's 4.2 divided by square root of 30. We end up getting approximately 3.39. A z-score is going to be probably between -5 and 5 and +5 at most. So if you end up getting a number outside of that, you may have done your calculation incorrectly, especially if it's like 1,000 or 100 or something like that. Generally, those values just don't end up happening here. So that's our test value. Step 3 done. Now step 4, we make our decision. So we're either going to reject h sub 0 or not reject h sub 0. Well, we compare our critical range and our test value. Our critical range is anything to the right of 1.65. Right? We found that in step 2. That was our z-score. 1.65 is that dividing point right there, essentially. And our test value, that's 3.39. You know, if 0 is right here, anything to the left of 0 is negative, anything to the right of 0 is positive, 3.39 would definitely be in the critical range. It would be somewhere like here. So it is in the critical range. So we'll say here, since the test value lies in the critical range, we reject h sub 0. So essentially, the data in the study was so convincing to the claim that we can go ahead and say the claim is probably true and we'll reject our original assumption. And so step 5, we just summarize everything. And as I mentioned, you can always summarize it with this exact same quote. At a significant level of alpha equal to 0.05, there is sufficient evidence to support the claim that the average, what were we talking about here again? The mean of their ages in a hospital for doctors. To support the claim that the average age of doctors in that hospital is greater than 46. Done. And that would be our completed hypothesis test for this question. Pretty good example. I hope this helps shed some light about how to do a hypothesis test. Again, step 1, we stated the hypothesis and the claim. Step 2, we found the critical range, the value that kind of is the cutoff for when to accept or reject h sub 0. Step 3, we found the test value computed from a specific experiment. 4, we decided whether to accept or reject by comparing the test value and the critical range. The test value is in the critical range, so we reject. And then our summary. Let's go ahead and do an example of a two-tailed test as well. Okay, so I've got another question here in the hypothesis test. It says, the Medical Rehabilitation Education Foundation reports that the average cost of rehabilitation for stroke victims is $24,672. To see if the average cost of rehabilitation is different at a particular hospital, a researcher selects a random sample of 35 stroke victims at the hospital and finds that the average cost of their rehabilitation is $26,343. The standard deviation of the population is $3,251. At an alpha of 0.01, can it be concluded that the average cost of stroke rehabilitation at a particular hospital is different from $24,672? So, they're telling us a significance level and to test something, so that means do a hypothesis test. Step 1, we state our null hypothesis and alternative hypothesis. Go ahead, try to figure it out. What is our null and alternative hypothesis here? Our null hypothesis, we're assuming that the mean is 24,672. Tells us that in the first sentence, it says that the population average is 24,672. And what are we testing? Well, it says at an alpha of 0.01 can be concluded that the average cost of stroke rehabilitation at a particular hospital is different from 24,672. So what does that mean? It's not asking us, is it greater than? It's not asking us, is it less than? It's asking us, has it changed? Is it different? Remember, that means we use a two-tailed test, aka the not equal sign. So in this case, our alternative hypothesis is that mu is not equal to 24,672. Remember, the key phrases are if it's an increase or a greater than, we use a greater than symbol. If it's a decrease or a less than, we use a less than symbol. if we're looking for a change or a difference, we use a not equal to symbol. Here it's asking for, is there a difference? Step 2, find the critical, in this case, values, because it's a two-tailed test. So, let's draw a picture. And our alpha that they're giving us is 0.01. So if our alpha is 0.01, the rest would be 0.99, aka 99%. So the two tails are going to represent 1% of the data. The rest, the non-critical range, represents the other 99% of the data right here. And there's going to be two tails. We've got a tail here and a tail here. And if there's only 1% of the data left to divvy amongst both tails, due to the symmetry, we cut that in half, and each of these tails would have to contain 0.5% of the data to get the last remaining 1%, to essentially encapsulate the last 1%. Right now our graph adds up to 100%. Our alpha is 0.01. Wait, yeah, 0.05%. So as a decimal, that would be 0.005, right? If you cut 0.01 in half, that's 0.005. And 0.005 plus 0.05 is the 0.01 that we have for our alpha. And so this will help inform us on coming up with the critical values. This critical value on the left, we have to look up the value that has an area closest to 0.005, right? 0.5% is equivalent to 0.005 area. You just move the decimal 2 spots to the left. And that's what we've got to look up on our z-table. Actually, I want the negative z-table here, sorry. So we're looking up the value closest to 0.005. Be very careful, you're not looking for 0.0005 or 0.05. You're looking for 0.005. And it would be either of these two values. They're both the same distance away. The book ends up settling on negative 2.58 rather than negative 2.57. But again, you could pick either one, or you could split the difference. So the book picks negative 2.58. So this value right here is a z value, I'll call it z1, of negative 2.58. The z value over here on the right is the positive of that. I'll call that z2. That's 2.58. It's the same value, just the positive version. So when doing a two-tailed test, just find the one on the left. The one on the right is going to be the same value, but positive. If you wanted to find it on the z-table, let me just do that as well. So for the value on the right, how much area is going to be to the left of that value? It's going to be 99.5% of the data is going to be to the left of that. So we've got to look for the value closest to 0.995. 0.995. You'll see here we do get the positive 2.58. So that's how to find the right tail as well. But as I mentioned, it's just going to be the positive of the one on the left. Okay, so that's our critical values and thus our critical ranges. Now we compute our test value. And we're using z-scores again because sigma is known. And our formula is x bar minus mu over sigma divided by square root of n. What's all the information here? Our mu is 24,672. What's our x bar? I don't know where to put the comma. Our x bar, so that's the average of the sample. That was 26,343. The standard deviation of the population, 3,251, and the number of people in the sample, n, is 35. Plug it all in. What are we going to get here? Again, I'll just round to 2 decimals, making sure to use parentheses for numerator and denominator. 26,343 minus 24,672 divided by 3251 divided by square root 35. We end up getting 3.04. There's our test value. 3.04. Now we'll decide whether to accept, to reject or not reject. Draw, well, you don't have to draw the picture for the, I guess it does help. You don't really have to, but I'll just go ahead and do it anyway. We have our 2z critical values here, negative 2.58 and 2.58. So any z-score in these, if our test value is in either of these orange regions, we're going to reject h sub 0. Our test value 3.04 is around here, which is in the critical range, right? So since the test value lies in the critical range, we reject h sub 0. So we've done all the work. We just got to summarize our results. And we can say at a significance level of 0.01, there is sufficient evidence to support the claim that the average cost of stroke rehabilitation at that hospital is different than 24,672. And that would be our completed hypothesis test. Okay, so I hope that makes sense for section 8.2. Again, it's just basically contextualizing the stuff that we've learned into a very formal experimental output, essentially. And we've, again, already seen the formula used here in step 3. We're just now contextualizing what these values mean and how to show that data to people, essentially. So let's go ahead and continue and look at section 8.3, which is on when sigma's unknown. And for that, we use a t-test. Okay, so again, in section 8.3, we're going to be doing hypothesis tests. So the same structure, the same 5 steps. The only difference is now that sigma is unknown, we're not going to be using z-tables. We're going to be using the t-tables. And we've got a formula, again, for the t-score. But again, we've already used these. And we've already used this formula. So nothing new. We're just putting it all together in hypothesis tests. So again, the formula for t is x bar minus s, because we don't know sigma, so we can't use sigma. We've just got to use the best estimator to sigma, which is s. Or I'm sorry, I put that in the wrong spot. Sorry. X bar minus mu over s divided by square root n. I put the, sorry, x bar minus mu over s, not sigma, divided by square root n. Again, the s was sigma when we know sigma, but if we don't know sigma, we use our best guess to sigma, which is s, the standard deviation of the sample. And remember, df is just n minus 1. So let's look at some examples. Okay, so we've got this question that says, a medical investigation claims that the average number of infections per week at a hospital in southwestern Pennsylvania is 16.3. A random sample of 10 weeks had a mean number of 17.7 infections. The sample standard deviation is 1.8. Is there enough evidence to reject the investigator's claim at an alpha of 0.05? Assume the variable is normally distributed. They have to do that because our sample is only 10. It's not big enough. So they have to clarify that it's normally distributed. Anyway, is there enough evidence to reject the investigator's claim at a significance level of 0.05? That means hypothesis test. Okay, so let's do the hypothesis test. So our null hypothesis, what are we assuming to be true? It's a little bit, the wording here can be a little confusing because they're using the word claims. That's a bit of a misnomer. That ends up being our mu, 16.3. We're assuming that the average number of infections per week at the hospital is 16.3. And then what are we testing? This one can be a little confusing. When making a claim, you're trying to see if your claim is wrong, and therefore what you're testing is is the claim different? Is it actually equal to something else? So in this one, it's going to be a not equal, and we're going to be using a two-tailed test. Again, another way to see this is it doesn't explicitly say anywhere anything about being greater than anything or being less than anything or increasing or decreasing. That lack of verbiage also kind of signifies that we're just testing to see if it's anything other than this 16.3. So that definitely can be a bit confusing. I guess when in doubt, if it's not saying anywhere you're testing for something bigger than or something less than, default to a not equal to sign and do a two-tailed test. So here we've got our step 1 done. And then step 2 is to find our critical values. There's going to be 2 here because it's a two-tailed test. And we're going to need the t-tables this time. What was our significance level? 0.05. It's a two-tailed test. So if the critical range should be equal to 5% of the data, the non-critical range would be the remaining 95%. If we've got 5% left to divvy up, this would be 2.5% of the data. This would be 2.5% of the data. To look this number up, we want to look up the area closest to 0.025. To this one, we want to look up 0.975. So let me get the t-tables. Okay, so I've pulled up the same t-table I had earlier. So our alpha is 0.05. So we can look up 95%. This is the column that we want here. And what's our degrees of freedom? 7. Wait, was it 8? No, 10, sorry. Our n our n is 10 here. So it's 10 minus 1, aka 9. Okay, so we end up getting, we're looking for 9. That's our degrees of freedom. Lining that up, we get 2.262. So we get our two t-values for the critical ranges. I'll call this t1. That's the negative of this. Negative 2.62, or sorry, I messed this up. 2.262. And this one ends up being, I'll call it t2. It's positive 2.262. So those are our critical values. Those will represent the boundaries of our critical ranges, I guess. Okay. This just happens to be a two-tailed test, right? But we'll look at a one-tailed test as well. So we've got our critical values and critical range. Let's now compute our test value. Since sigma is unknown, we use the t formula. X bar minus mu over s divided by square root of n. Identifying all this information, what do we get? Mu, sorry, I've got to scroll back to where I was. Mu in this case, we're assuming to be 16.3. The average of the sample is 17.7. The standard deviation of the sample is 1.8. and the number of weeks in the study was 10. That's our n. This gives us the following t. And I get approximately 2.46. That's our test value. Step 4, we either reject or not reject h sub 0. Let me draw this picture. Remember, this t value is negative 2.262. This one's positive 2.262. The test value we got was 2.46, just a little bit shy of being in the critical range. Our test value. So since it's not in the critical range, wait, sorry, it is. I messed up the number again. Sorry guys, sorry. This is 2.262. So it is in the critical range. 2.46. Is in the critical range. Okay, so again, we reject h sub 0. Finally, our summary. At, what was our significance level again? 0.05. There is sufficient evidence to support the claim. And so the claim that they made, since we're essentially rejecting our null hypothesis, we're rejecting the claim that the average amount of infections is 16.3. Hope that makes sense. Okay, so I've got another question here from the book. It says, medical researchers found that the people who take aspirin take on average 8.6 tablets a week. A medical doctor wanted to see if he could reduce the number of aspirin tablets a person consumes if the subjects practice yoga twice a week. A random sample of 12 people who take aspirin were taught yoga, and after a 12-week period, the doctor found that they took the following number of tablets for 1 week. And there's the data. And it's asking, test the claim at a significance level of 0.1, assume the variable is normally distributed. To save us the time of calculating this x bar, I'm just going to let us know x bar is 6.8. Also, the standard deviation, to save this calculation, is 2.37. But we discussed these months ago. in the very early chapters of how to calculate the mean of a sample and the standard deviation of a sample. So if you've forgotten those, make sure to go back to the previous notes. I guess it's under chapter 1, I think. So, okay. Step 1. What do we end up getting? Well, it looks like our null hypothesis we're assuming that the average is 8.6, and we want to test that after they're taught yoga if it goes down. So we're testing to see if it's going to be less than 8.6. See, because it says the medical doctor wants to see if he could reduce the number of aspirin tablets a person consumes if they practice yoga twice a week. So he's trying to test if the yoga actually does decrease it to a significant enough amount. Step 2, find the critical value or values. Our alpha in this case is what? 0.1. It's going to be a left tail test here. Since our alpha is 0.1, this is going to be 90%. This is going to be 10%. So when we're looking this up on the chart, this value of, well, actually, yeah, I guess that value is not important for the t-tables. Sorry about that. So we got to go ahead and look up the t-table. Find the critical value. Okay, so we've got to interpret a little bit differently because of it's a one tail test. It's much better to use these columns instead of the one that I used at the bottom in the last example. So my apologies there. Did end up being the right way for two tails, though. Kind of just can't always use that same way when it's one tail. So we've got to look at one tail, and this is talking about alpha. So in this case, our alpha is 0.1. And what's our degrees of freedom here? 11, because 12 minus 1, we get 11. There's 12 people in the study here. So our degrees of freedom is 11, so it ends up being 1.363. It's going to be negative of that, though, because it's on the left. Let me just go back to the last one real quick. The two-tail lines up with the confidence interval at the bottom. Not for the one-tail, though. So I guess to be safe, just always use the top column. For two-tail, use this one and line it up with the right column. So let me go back and change it. Let's use this column instead. For the last one, I'll erase this one here. And for here, this one. Okay, now that's fixed. Sorry about that. So our t-value in this case, negative 1.363. Now we find the test value. Just plug everything into our formula. What do we get in this case? Our x bar is 6.8. Our mu is 8.6. Our s is 2.37. And our n is 12. ends up being approximately negative 2.63. That's our test value. And I think this one does lie. Again, we end up rejecting every single time here. I should probably pick an example where we don't reject, but I guess not the end of the world. So our cutoff of the critical range was negative 1.363, right? Yes. I think I said it wrong. 1.3. No, I said it right. All right. And our test value ended up being negative 2.63, which is around here. And that is in the critical range. So again, we're going to reject h sub 0 because our test value lies in the critical range. And so we can summarize. We can say there is, at the significance level, there is enough evidence to support the claim that practicing yoga reduces the weekly aspirin intake. Blah, 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 blah. Okay, so I hope that makes sense for t-tests for the mean. I guess the only thing I'd like to clarify again is when reading the t-tables, use the top columns. Make sure you're in the right row for one tail or two tail when looking up the significance level column. And then you line up with the degrees of freedom row with that column to get the t-value. If it's on the left, if it's a left tail test, you've got to make the t-value negative. If it's a right tail test, you make the t-value positive. And finally, the last section that I'd like to cover here, 8.4, is on z-test for the mean. For proportion, sorry. Sections 8.5 and 8.6 are just more hypothesis tests for more topics. And, this is going to be our third example of different types of hypothesis tests. If I think at this point, essentially we'll have gone over enough. Whereas if you need to do another type of hypothesis test, you would just have to figure out how to calculate the critical values and the test value. Anyway, remember we also talk about proportions quite often. In this case, to compute our test value, we're going to be using the formula z is p hat minus p over square root of pq divided by n. This is going to be our z-score for proportions to come up with the test statistic. And we'll use the z-tables to come up with our critical values again. Okay, so example or two. Okay, another question here. A researcher claims that based on the information obtained from the Centers for Disease Control and Prevention, 17% of young people ages 2 to 19 are obese. To test this claim, she randomly selected 200 people ages 2 to 19 and found that 42 were obese. At a significance level of 0.05, is there enough evidence to reject this claim? So we're going to be using a two-tailed test for this one. Again, it doesn't say greater than or less than anywhere, anything like that. So we're just going to be trying to see if it's different than this. So for our step one of stating the hypothesis and the claim, our hypothesis, we're assuming that the population proportion is 17%, aka 0.17. We're trying to see if it's different than that. So we're trying to see if it's not equal to 0.17. Step 2, find the critical values. Let's draw a picture. It's a two-tailed test. Oh man. Two-tailed test. And our significance level is 0.05. So if 5% of the data is in the critical range, that's what's signified by alpha being 0.05, the non-critical range would be 95% of the data. That means this would be 2.5% of the data, and this would be 2.5% of the data, because we have to cut the remaining 5% in half. So let's look up the one on the left. To look up the one on the left, we're going to look up the value that gives us the area closest to 0.025. So where's my z table? So I'm looking for the area closest to 0.025. That will tell me that value on the left. This one right here, negative 2.81. Oh, I made that mistake I told you guys not to make earlier. I'm looking for 0.025, not 0.0025. 0.025 is right here, actually. Sorry about that. Negative 1.96. That would be the boundary of this critical value. That's negative 1.96. And this one is positive 1.96. And if you wanted to look it up on the table, you would look up the area closest to 0.975, because the area to the left of that point is 97.5% of the data. So we found our two critical values. Step 3, we calculate our test value. So the formula here, remember, is p hat minus p over square root of pq divided by n. Let's identify all that information. They tell us in this question we're assuming that the percentage of obese people ages 2 to 19 is 17%. That's our P, the population proportion. Remember, P hat, that's the sample proportion. So since she selected 200 people and 42 of them were obese, we do remember 42 over 200. And let's cut it off with 2 decimals. Let's leave everything with 2 decimals, but I think this is only 2 decimals anyway. 0.21. That's our P hat. So we know P, we know P hat. We also need Q. Remember, Q is just 1 minus P, which is 1 minus 0.17, aka 0.83. and n is, oh yeah, 200. Okay, plugging it all in the formula, right? Our p hat, I guess I'll just rewrite everything here. P is 0.17, p hat is 0.21. Well, I'll put q next. P is 0.17, and so q is 0.83. P hat is 0.21, and n is 200. So what do we get for our test value here? .17 times 0.83 divided by 200. And I'm getting approximately 1.51. It's our test value. And finally, we get an example where we're not going to reject. And so it does look like in this case that our test value does not lie in either of the critical ranges, which are divided by negative 1.96 and positive 1.96. Ends up being around here. So in this case, we do not reject h sub 0. And so we would say at an alpha of point, what was it again? 0.05. We do not, I'll say there is not enough evidence to reject the claim. Okay. I guess we could do one more, and that'll be it for the video. Okay, so last question of the video here on our hypothesis test review. It says a statistician read that at least 77% of the population oppose replacing $1 bills with $1 coins. To see if this claim is valid, the statistician selected a random sample of 80 people and found that 55 were opposed to replacing $1 bills. At an alpha of 0.01, test the claim that at least 77% of people are opposed to the change. You know, guys, let me change this one. I believe that one is outside of the scope of what I want to talk about in this question, or in this, basically, I think that one used one of the operators that we didn't discuss. We're only talking about less than, greater than, or equal to here. So let's try this one instead. My apologies. Let's not use the p-value method, though. Told you guys. I really hate the p-value method, honestly. I think it just causes a lot of additional confusion. So this one instead, yeah, this one's better. An attorney claims that more than 25% of all lawyers advertise. A random sample of 200 lawyers in a certain city showed that 63 had used some form of advertising. At an alpha of 0.05, is there enough evidence to support the attorney's claim? So our H sub 0, he claims that it's more than 25%, so let's assume that it is 25%. And then we'll be testing to see if it's more than 25%. So our critical values, I guess value in this case, it's going to be a one-tailed test. Our alpha is 0.05. So we want this to be 95% and this to be 5% of the data. I guess we can look up the right Z table. And we're going to look for the area closest to 0.95. So the area to the left of this value is 95%, aka 0.95. So remember, it's one of these two, but we go with 1.65 for consistency. That's our critical value. Test value. We use our formula p hat minus p over square root pq over n. What's everything here? Our p is 0.25. Our p hat. So what's it say here? He did a sample of 200 lawyers and 63 said yes. So that's 63 over 200. .315. I'll just leave it as 0.315. I don't want to round that. Just one more decimal, not a big deal. What else do we need? Q. Well, if P is 0.25, Q is 0.75. It's just the complement. And our N is 200. .315 minus 0.25 divided by square root 0.25 times 0.75 divided by 200. 2.12. That is our test value. Do we reject or fail to reject? Or, I'm sorry, I always say that, but I don't like it. So I want to say, do we reject H sub 0 or do we not reject H sub 0? Our critical range is anything to the right of 1.65. And our test value 2.12 is going to lie in that. So we're going to reject H sub 0. And finally, our summary at an alpha of, what was this, 0.05. We do have sufficient evidence to support the claim that more than 25% of lawyers in the city that they're in use some form of advertising. Okay, so that concludes our Chapter 8 review on hypothesis testing. I hope this was a good review. Please feel free to email me if you have any questions, comments, concerns, as always. And thank you very much for watching, and I'll see you all in the next set of videos. Have a great rest of your day.